This is Byron Scott. I'm going to be presenting my uh, high-level concept for a machine learning system to determine optimum driving speeds for all typical speed zones. So the problem really stems from fuel efficiency being an issue for really anybody that has a gas-powered vehicle. Um, Continuous fuel efficiency is not really something that is on most people's mind when they're driving their car. The things that dictate how fast a car goes really are the flow of uh, the rest of the traffic and the speed zones that have been determined by the government. Those speed zones don't necessarily correspond to the fuel efficiency ratings that are listed on a brand new vehicle when you buy it from the car lot. When you buy a car from the car lot, they list the city rating and the highway rating. But in reality, there's a lot of different speed zones ranging from school zones, which are very slow, to full speed driving on the highway, then all the ranges in between there. Now, in order to really achieve uh, overall fuel efficiency, there are likely optimum speeds in each of those speed zones where, if a vehicle followed the um, optimized recommendation, a owner would likely realize a decent amount of reduction in money spent on fuel. ML is a really good fit here. Um, there are probably thousands of different environments, and by environments, I mean different makes, models, and years of vehicles that would potentially be analyzed by this system. In addition to the different number of environments, there's a lot of continuous incoming data that would need to be analyzed pretty much continuously, and and if possible compared to other vehicles of the same make and model. Um, I think the customer interest is is pretty obvious. If there's daily small savings and money spent on fuel, that's money back in the pocket of everybody that owns or operates a gas powered vehicle. Like I said, the problem is continuous fuel efficiency is not really what is on people's minds when they're driving and operating a vehicle. The things that govern um, this type of stuff is the uh, government posted speed zones and the price of a gallon at the time of purchase. Outside of that, and most drivers don't really think about the difference between, say, driving 68 miles an hour versus 73 miles an hour. And then that's really another driver there is personal schedule, but it's not money um, spent on fuel. So today, a lot of vehicles do report a number for fuel efficiency. There's usually a couple. You can, flip through the dashboard and see that there's this, realized miles per gallon, which is really the fuel, how many miles per gallon that the car has achieved since the car existed, or since that button was reset, which is a long-term average, and that is not specific at all to the place that you're actually driving at that time, which is where the speed zone comes in. There's another value there that is that you can get to in most vehicles is an instantaneous fuel efficiency. In my experience, that number seems to go all over the place, and I haven't seen much useful come out of that. Yeah, so the goal would be to, um, build a model that results in continuous recommended driving speeds for that is based on observations from your specific vehicle in these given speed ranges. Um, there's, we'll get into the details of how we would achieve that in a few minutes. So I don't know that it's a limitation, but up front, we would have to work with the vehicle manufacturers to access most of the data that we would need in order to achieve this model. I'll go into the features in just a few minutes. Um, that's the goal, is a model based on observations from an operator's actual vehicle that tells them in this known speed zone what speed you should drive at to be the most fuel efficient. Now, the types of the data that we're going to need for this is there's several features that we would definitely need. I can see expanding to all kinds of things that I will mention later on in the last slide. The first thing that we need is the speed zones themselves. The model would need to know how fast needs that information to say, this is the range that you can be driving, because we obviously can't just put the most um, you know one speed out there to cover all speed zones. 55 miles an hour is not going to work for a school zone. Um, this information is publicly available. It's listed on the dashboard in my car. It probably is in almost all new cars these days. That's very easy to get. The model would also need access to fuel remaining and fuel capacity, which would be provided by continuous feed from the vehicle itself. Another factor is fuel grade, and I mean, octane level, 87, 89, 91, 93, if it's mixed with something, if it's got ethanol, things like that. There's a handful of ways I think that we can get to this data. I don't know enough about the vehicle sensor in this area to know whether the vehicle knows what it's burning, but that may be there. We could also just make an assumption at the beginning and use the most common, which is probably 87 octane, or if we have the fuel remaining information and that goes up, and we have the capacity, and we know that maybe we know that it's full, we could ask the operator to tell us what type of fuel that they input. I did list here that potentially we could get that from the receipt at the time of purchase, but I don't think all those are created equal. Obviously, we're going to need the vehicle speed, instantaneous vehicle speed. Didn't list it here, but we also need the odometer reading as a continuous feed in order to prove that the model is actually useful and is saving people money. We would need the manufacturer speed ratings, and those probably go all over the place. But we'll start with the simplest ratings, like the city and highway ranges. And other data that would be very beneficial would be the same feature set for vehicles of the same make, model, and probably year. We could figure out down the road if how much the year mattered. The type of engine or some other hardware issues may be a bigger factor. But Other data from other vehicles would be used to um, train the model initially. So you had a starting point, that when you drive it off the lot, for example, there hasn't been any local observations from that vehicle, so the vehicle would need a place to start. And then once it started, we would start training using the local observations. Down the road, the data from the other vehicles could be run through our model to see how the vehicle and the model are performing versus the other vehicles as well. A note here, as there's going to be continuous data logged, one situation that's not really applicable but would be part of the data set is stop and go traffic. And there's probably another situation, but stop and go traffic in particular is not really useful in this situation as far as I can tell. So that will be part of the data set, but that data should be quarantined, and we could determine that pretty readily. I mean, if the vehicles under some uh, speed threshold for X amount of time, then that data should be quarantined and not used for um, training or testing really. Now the last bullet down here, there's other factors like vehicle maintenance, how long it's been since an oil change, how long it's been since spark plugs were changed, um, what the tire pressure is, what the um, what's the temperature outside, things like that, that we could get into later on. But at a minimum, a marker for um, the vehicle maintenance milestones so that we could keep up with the health status of the vehicle at a minimum, not completely in detail, but at least vehicle healthy or vehicle not healthy could be useful at first. I imagine the overall vehicle performance would change over the life of, say, an oil change. Okay, so for the model itself, this would need to be an Edge AI solution. The model runs on the vehicle. There's no need for any cloud implementation, but other than when the model is initialized, and potentially some to reach out to do some comparison against similar vehicles down the road. But on a day-to-day basis, there is no need for cloud involvement. The data and hardware, everything is on the vehicle itself. Online training would be required. Like I said, the model itself would either be initialized with using the values from the manufacturer, or um, that aggregate solution from similar vehicles, but not the local observations. It's going to just take some time to get the local observations. So online training would be necessary, as well as online predictions. When you're driving in a typical commute, um, or wherever you're going, the speed zones that you drive through change many times typically. So anything outside of those zones themselves can change values. If there's construction or something like that, an interstate, um, some stretch of the interstate can drop from 70 miles an hour to 40 miles an hour or 55 miles an hour or whatever. But the speed zones themselves can change, and they can change temporarily. So online predictions would be definitely be necessary. As far as uh, the technology decisions, the main Python analysis tools um, as much data analysis as would need to go on here. That seems like, up front, that would be a good decision. But I think the required interaction with numerous different vehicle manufacturers could facilitate another decision. We would need access to the API um, to support getting to um, the vehicle information, the fuel used, distance covered, instantaneous speed, all that stuff, and what those APIs look like could steer what the other, you know, what the language of choice ended up being. Uh, but having said that, open source would, anywhere possible, would make the most sense. Just if for no other reason that there would be, you know, as other manufacturers are supported, there's potential to be some cost in getting access to the data from the vehicle. So, cost savings in any other area would be great. Okay, so model evaluating the model. The goal here is to refine the manufacturer ratings and make it more to get to a more granular recommendation, so that we're, instead of talking two ratings from the manufacturer, now we're talking, probably 7 to 8 different speed recommendations to achieve that similar type of high rating that the manufacturer reports when you buy the car. Um, so the model itself um, should be compared against the manufacturer's model, and it should also be compared um, with similar with the data from similar vehicles to confirm that the model itself is valid and that the vehicle is performing consistently, and vice versa. So that the data from our local vehicle should also be compared against the models derived from observations on other vehicles. So we get some cross training and cross validation by comparing, but by leveraging the data that is acquired on two different but similar vehicles. Down the road, is after initial deployment, like I mentioned earlier, I think possibly a lot of other critical features that could be added, like the type of oil, air temperature, tire pressure, relative humidity, really just to name a few. So I think after model deployment and some iterating on additional features, those could be um, deployed in future iterations. There's some risk here. I'm sure that there are more than I have listed here, but it's possible that we couldn't get access to all of that information. It seems like we could, because it's being displayed in the dash, but it's possible that some of that information is proprietary and vendors just don't even. It's not even a possibility to get it. Um, it's possible that the interaction with all those manufacturers is just too high. That's probably, I that's a huge risk. And the third one is the biggest risk, and that is that we put this model in place, um, make these speed recommendations. People start, the drivers follow them, and it turns out, it just wasn't that big of a difference on the pocketbook. I think that risk is probably pretty low, but that would that would be the nail in the coffin on the model. But that's my presentation. Thanks for listening.